Welcome back, everybody. Today we're going to be doing section 6.3 star, and we're going to kind of continue with what we were talking about last time. So last time in section 6.2 star, we defined the natural logarithmic function and then a bunch of properties of the logs that fell from that definition. And now we're going to define the natural exponential function. So let's get started. Let me pull up the slides. Here we go. Oh, move this out of the way. So here's the overview. We're going to define the natural exponential function in a natural way. Then we're going to look at some properties of the natural exponential function. Then we're going to see how we can extend the function e to the x to irrational numbers. And remember, e is that number that makes the natural log equal to 1, right? So e is a number. I know that sounds weird, but e is a number. And we're going to see how raising that number to the power of x can be extended to irrational numbers. Then we'll do a couple examples. Then we'll talk about the laws of exponents. We'll get all the laws of exponents next. Then we'll talk about how to differentiate e to the x and how to integrate e to the x. So let's get started. Quick review. If you remember in the previous section, we defined the natural log function as this area so far function, the area from 1 to x under the curve 1 over t. So one thing to note about this particular function, the function is strictly increasing. Why is that? Think about that for a minute and see if you can figure out why we know that this function, the natural log of x, is strictly increasing. All right, now say it out loud. Why do you think it's strictly increasing? All right, I think the easiest way to explain it is if you imagine that curve that you're finding the area underneath, this is the curve 1 over t, right? Here's 1, here's x. Well, what's happening is you're basically adding more and more and more area as x moves along, right? So as x increases, the area under that curve increases. You're basically adding a little bit of area at each step, a little bit more, a little bit more, a little bit more. So what happens is that area is strictly increasing. Therefore, the natural logarithm function is strictly increasing. And there's an important result from pre-calculus that says if your function is strictly increasing, then your function must be one-to-one. And consequently, it has an inverse. Now that's an incredible result here because what this means is that our function, the natural log function, the one that we defined in the previous section, this right here, it must have an inverse. So this area so far integral has an inverse function. It does exist. So we're going to define that inverse function to be exp of x. So we're defining the inverse of this log function, which we know exists, to be exp, the natural exponential function. So more specifically, we say that y is equal to exp of x, if and only if ln of y is equal to x. So that's how it's defined. So now notice we've kind of gone reverse from what you saw in pre-calculus, but it does work. It works. Now we can get the natural exponential function. As a result, we get the cancellation equations. So the cancellation equations are if you take the exponential of the log, you end up with x. And if you take the log of the exponential, you end up with x. So that's what the cancellation equations look like now in this case. All right, some properties of this exponential function. For one, we know that exp of 0 is equal to 1 because as we showed in the last section, the natural log of 1 is equal to 0. Remember that inverse functions invert the domain and range, so inputs and outputs get switched. So here, natural log of 1 is 0, therefore exponential of 0 is 1. Inverses, right? We also know that exp of 1 is equal to e. Why is exp of 1 equal to e? Because as we saw, the number e is the number that makes that integral equal to 1. So in particular, natural log of e is equal to 1. So remember, e was that very, very special number. It's that number that makes that area equal to 1. And now what we're showing with this result is, hey, the inverse of this function, this exponential, if we evaluate it at 1, we get that special number. So the natural exponential evaluated at 1 is equal to e, which is nice. A cute result, right? Oh, I also have this picture over here. So if you remember from section 6.1 or just from maybe a pre-calculus class, the graphs of inverses are reflected across the line y equals x. Wait, for you all, it's this way. Yeah, right. So inverses are reflected across the line y equals x. So this was the graph of the log function that we saw in the last section. So if we want to graph the exponential function, we're going to reflect, and we'll get that. So it looks like you would expect, like what you've seen in the past. Some other properties, the domain of the natural exponential is all real numbers because the range of the log function is all real numbers. And correspondingly, the range of the exponential function is all of the positive numbers for the same reason. We also know that the exponential function is continuous because the natural log function is continuous. Why is log continuous? That we actually saw in the previous section. The natural log function is continuous by the fundamental theorem of calculus, or maybe more immediately you could think, well, it's differentiable, therefore it's continuous. But this is an important thing too. This is a result from pre-calculus as well. If a function is continuous and it's invertible, then its inverse function is also continuous. So everything is working out really, really nicely here. Okay, now that we have this all set up, we can extend that function e to the x to irrational numbers. So if r is any rational number, just like a rational number, like a fraction, a ratio of two integers, then we can use the properties of logarithms from the previous section to get this result. Oops, sorry, this result right here. So this is actually one of the laws of logarithms from the last section. So ln of x to the r is equal to r times ln of x for any positive x, right? Well, if we set x to be this number e, this special real number e, then this thing becomes ln of e to the r. And so we get that ln of e to the r is equal to r times ln of e. But we just showed a minute ago that ln of e, or not even a minute ago in the previous section, ln of e is equal to 1, so we get r. So in essence, what we just showed here is that the natural log of e to the r is equal to r. That's it, for any rational number r. So we can use the cancellation equations that we just talked about a moment ago to get this result. The exponential of r is the same as taking the exponential of the log of e to the r, and by the cancellation equations, we get that that's equal to e to the r. All right, so let me highlight something here. What's happening with these steps is that we just showed that our exponential function that we just defined today is equal to this function, e to the r, for any rational number r. All right, so remember, e is just a number. So e to some power is a function that's like that. The exponential function is the inverse of the logarithmic function. And what we just showed is that this exponential function is equal to the function e to the r for every rational number. But we also know, yeah, that's what I'm saying right here, this piece right here. But we also know that the exponential function is continuous on all of r. So the exponential function is continuous everywhere because the log function is continuous everywhere by the fundamental theorem of calculus. So because the exponential function is continuous everywhere, we can now define the exponential function, or sorry, we can define the function e to the x as the exponential function on the irrationals as well. All right, so this is the elegant result that kind of ties everything together. We started with the natural logarithmic function defined as that integral. Because of the properties of that integral and the fundamental theorem of calculus, we end up getting that you can define its inverse as well. And its inverse is defined as the exponential, but then it turns out that this inverse is also just equal to e to the x. It's just equal to e to the x everywhere else. Pretty cool. Pretty cool stuff. All right, so now we get this. So we can now say that the exponential function is e to the x. So it agrees with that intuition that you got back in pre-calc or algebra when you were first talking about the natural exponential. Using this new notation, we can also rewrite the cancellation equations. So, oh, and our definition. So now the definition is this. E to the x equals y if and only if ln of y equals x. This is what you saw back in algebra, right? This is what the cancellation equations now look like. E to the ln of x equals x for positive x's, and ln of e to the x equals x for any real number. Any real number. There you go. Everything just falls right out. Everything falls right out. Some other things that are going to fall out. This. So for one, we know that e to the x is also strictly increasing. We also know that the limit as x goes to negative infinity of this function is 0. And the limit as x goes to positive infinity is positive infinity. So we get that it's strictly increasing, we get its limits, its end behavior, and then, oh, I'm jumping the gun a little bit. Haven't got to the properties of the exponents yet. Okay, we'll wait till we get there. Let's do some examples first. All right, this is going to sound maybe a little too easy if you took pre-calc recently, but now that we have the inverse of the log function, we can solve logarithmic equations using the exponential function. So what is x if the natural log of x equals 5? Well, if ln of x equals 5, that means x equals e to the 5. There we go. Easy enough. What are we using here? We're simply using the definition of an inverse function. That's it. Definition of an inverse. How about this one? Solve this equation. See if you can do this one. This will kind of refresh your memory a little bit about stuff you might have seen before. Try to solve this equation for x. Go for it. I'll just jump right to the thinker and the writer. Try to work it out on your own, and then we'll do it together. All right, let's do it together. So first thing is we can use the definition of inverses to invert the function, or sorry, to invert the equation and write it in terms of log. So if e to the 5 minus 3x is 10, that means ln of 10 is 5 to the 3x, or 5 minus 3x, right there. Then you can do some basic arithmetic and solve for x, and you get that. Not too bad, right? Not too bad. Okay, how about this one? So this is what I want you to think about and then try on your own, and then we will do it together. So what would you do first to try to calculate this limit? Think about it for just a minute. Okay, now say something out loud. What are you thinking? Remember, you can say anything you want to your dog, to your sister, to your brother, to the wall, whatever. What would you try first? All right, now try it out and see what you get. See if you can compute this limit. All right, now let's do it together. So we're going to use a familiar technique, a technique that you learned back in Calc 1 when you have to deal with limits of rational functions. And we're basically going to divide by the highest power term. That's really what we're going to do. So in this case, the highest power term, quote unquote, is e to the 2x, right? There's an e to the 2x in the top, and there's an e to the 2x in the bottom. So if we divide the top and the bottom by e to the 2x, it will allow us to deal with this infinity over infinity situation. So here we go. Divide the top by e to the 2x, divide the bottom by e to the 2x. E to the 2x minus 2x is e to the 0, which gives you 1. And then 1 times e to the negative 2x is just e to the negative 2x again. Okay, let me erase this real quick. All right, now we can actually push the limit operator inside the fraction. So we can take the limit of the numerator and the denominator separately, right? Now that we're not going to get some kind of infinity over infinity situation. And we can move the limit operator into this term right here. And we just saw that this limit is equal to 0. So the limit as x goes to infinity of e to the negative 2x is going to be 0. So we get 1 over 1 plus 0, which is 1. There you go. So now we can do things like that. The technique is pretty much the same. You just divide by the highest power term again. In this case, it's e to the 2x, or you could think of it as e to the x squared. That's another way of thinking about it. All right, now we can get the laws of exponents. laws of exponents. So this works for any real numbers now. We established that, but this is what you get. And this is going to look very, very familiar. Maybe you might even think it's a bit trivial, but now we actually have these results based on what we first defined as the natural logarithm. So if you have a sum in the exponents, you can write it as a product, e to the x times e to the y. If you have a difference in the exponent, you can write it as e to the x over e to the y. And then here, when you have a product, or I should say, when you have an exponent raised to a power, it becomes a product. There we go. That's it. Uh, this may seem like a little trivial, but you got to remember that it's only right now that we were able to establish that these laws hold for all real numbers. Technically, we've only known that they hold for rational numbers, but now we can establish that they hold for irrational numbers as well. And also, technically, we have only established this for the number e. We have not established it for any arbitrary base like 2 or 3 or pi or whatever. That we're actually going to get in the next section, 6.4. The proof, I'm going to skip the proof. You might have seen proofs like this before back in a pre-calc class, but the proofs just use the laws of logarithms. So in essence, you take this and write it in logarithmic form instead, and then you'll be able to use the laws of logarithms to derive this result. So I recommend trying that as an exercise on your own. I'll give you the beginning of it. You could say, let z equal e to the x plus y. So start with that, take the log of both sides, and then work from there. All right? Okay. Now we get a pretty cool result. So differentiating the natural exponential function. So this exponential function, e to the x, is incredibly unique. It is a very, very unique function. In particular, the derivative of e to the x is e to the x. So the derivative of this function is itself. It is itself. And we're going to see that this is basically the only function that behaves that way. In fact, that's what I say right here. The exponential function is its own derivative. And we're also going to see in the future that if you have this property, as in if you've got a function that is its own derivative, then it must be the exponential function, except maybe multiplied by a scalar, maybe like on the input or the output multiplied by something. But this function is the unique function that has this property that is its own derivative. And if you've got a function that is its own derivative, it is this function up to scalar multiples. So that's a pretty amazing result. The one, let's see, will we prove this one here? We will. Yeah, we will prove this one later on. We'll prove this one later on. But for now, just take it as the derivative of the exponential function is itself. And we're going to prove that right now. So here's the proof. First of all, we know that the exponential function is differentiable on the entire real line because its inverse, ln of x, is differentiable. And from section 6.1, we had that theorem that said, hey, if a function is differentiable, then so is its inverse. But moreover, this function has a non-zero derivative for, let me get my laser here, for all positive x's, right? So the derivative of e to the x is non-negative for any, or I should say it's positive, not just non-negative, it is positive for, I shouldn't say that. No, I apologize. I'm mixing my words. E to the x has a non-zero derivative for all positive numbers. There we go, finally got it out. So because of that, we can apply the inverse function theorem, and the inverse function theorem applies at every single point in the real numbers. Pretty cool, pretty cool. Now, we can write y equals e to the x, and then we can use logarithmic differentiation. So we're going to take the log of both sides. This means ln of y equals x. Yep, and then we can differentiate implicitly with respect to x, just like we did in the previous section, and we'll get this. Derivative of ln of y is 1 over y times dy dx. Derivative of x is 1, and then solving for dy dx gives us this. So the exponential function is its own derivative. Pretty wild. Okay, let's see. Next. All right, so you try to do this one. I'm going to let you try to do this one on your own, and then we'll do it together. So what would you do to differentiate this function? Think about it and then say something out loud to yourself. How would you try it? All right, now you try to work it out on your own. See if you can compute the derivative of e to the tangent of x, and then we'll do it together. All right, here we go. So we're just going to use the chain rule, but now we know what the derivative of e to the x is. It's its own derivative. So using the chain rule, we get that the derivative of e to the tangent x is going to be itself times the derivative of the inner function tangent of x, which is secant squared. So this is it. Easy peasy. Easy peasy, quick. All right. Now, how do we integrate the natural exponential function? Well, since we know that the natural exponential function is its own derivative, it follows that its integral is just itself as well, but perhaps shifted by some constant c. Pretty cool. Why is that? Because if I were to differentiate this thing, I will get e to the x. Therefore, an antiderivative of e to the x is itself also. Nice. All right, now we can do stuff like this. So here's another one. I want you to try to do this integral on your own. Maybe you can kind of see what you're going to use first, but think about it for a minute. Say something out loud about how you will approach it, and then we'll do it together in a minute. All right, try to do it yourself. Okay, now let's do it together. Let's see, looking at the function outright, it looks like we're going to need a u substitution. What I see is I see x cubed here and I see x squared here. And the derivative of x cubed is x squared. So, there we go. Let's do a u substitution. Let's let u be equal to x cubed. Then du is equal to 3x squared dx, so we just need to divide by 3 and substitute. And we get this. But as we just saw, the integral of e to the x is just e to the x again, so we get this. And then because this is an indefinite integral and we started with x's, we need to provide a final answer in terms of x's too. So we get 1/3 e to the x cubed plus c. That's it. All right, so let's play. Now we're going to do an activity related to this section, 6.3 star. And the next section is 6.4 star, where we basically just cover generalizing all of this to arbitrary bases. So it seems a little bit pedantic, but we haven't actually proved any of this stuff for an arbitrary base, arbitrary positive base, like 2 or 3 or something like that. So we're going to do that in the next section. All right, but I'll stop rambling. Thank you all for listening again, and I will see you next time. Test, test, test.